Hello dear students, let us continue with our discussion on the improper integrals. So I had given you a few exercises, so let us try these things. Say for this one, problem number 8, integration 3 to 5 x square dx by root over of x minus 3 into 5 minus x. Okay. So for this, you see that if you compare the denominator, okay, the denominator here is actually x minus 3 into 5 minus x. So this integral becomes improper at x equal to 3 and at x equal to 5, okay, because it will have points of infinite discontinuity at 3 and 5, okay. Also together with that, so here you see it's from 3 to 5. So and it's written as x minus 3. So x in the interval 3 to 5 is actually greater than 3. Okay. And this 5 in the interval 3 to 5 is greater than x, greater than or equal to x. Okay. So that is why it is written as x minus 3 into 5 minus x. Okay. If we write it as x minus 5, in that case this one 5 minus x quantity will be negative, so that it cannot be under the root. So it is in the form x minus 3 into 5 minus x. Okay. So we can split this because there are 2 points of infinite discontinuity. We can split this integral into 2 parts. Okay, one part is 3 to 4 x square dx by root over of this, and another part is 4 to 5 x square dx by root over of this. Okay. So what happens is for the first one I1, it has only 1 point of infinite discontinuity, that is at 3, and for I2 it has only 1 point of discontinuity at 5. Okay. So we will apply our process that we consider the integral from 3 plus epsilon to 4, okay, because it's the lower limit here. So it's from 3 plus epsilon to 4. We will evaluate that and then we will take limit with as epsilon tends to 0. Okay. So 3 plus epsilon of this, if you just simplify, what you have to do is you have to multiply this and you have to express it something like a square minus x square form, okay, or x square minus a square form, okay, like that. So 3 plus epsilon to this, if you just see, I can write it as 1 minus so the intention or the motive here for me is that this should be a perfect square. This expression with x square minus 8x, something like that, it should be a perfect square. So x square minus 8x, that means that x square minus 2 into 4 into x. So I need a 4 square term here. So I have added 16, but originally I had originally I had only 15 here, okay. So this, to adjust that, I have to give one plus 1 here, because this is minus 16, so minus 16 plus 1 is minus 15. So this can be written as 1 minus 4 minus x whole square, right? And then we can evaluate this by, so I have made a simple substitution here, that I have put 4 minus x equal to t. Okay, so this will give you 4 minus t whole square, and the limits will change. Okay, so that I have actually simplified the denominator. Okay, so I have written it as root over of 1 minus t square. Okay, so it's easier to simplify then, right? So the limits will change when x is 3 plus epsilon, your t will be 1 minus epsilon. Okay, and when x is 4, t will be 0, and also you will have dx is minus dt. Okay, dx will take the form of minus dt, so it's minus of 1 minus epsilon to 0 of this. Okay, and then we can write it as 0 to 1 minus epsilon of this quantity. Okay, so 4 minus t whole square, again we simplify and write it in this form. Okay, so that we can apply the formulas for root over of 1 minus t square. Okay, 1 by root over 1 minus t square, those formula we can apply. Okay, so here you see we have made a modification here, 16. If I just separate it out as again t square by this, then I will not be able to integrate it. Okay, if I separate it as t square by 1 minus t square, okay, then I will not be able to again integrate it, right? So what I do is I have to I convert it in the form of 1 minus t square. So for that actually I do something like 1 minus t square. Okay, so this is what I have done. So here it's 16, so you see I have written 17 here. Okay, so it's 17 minus 1 minus t squared and minus 8. Okay, so then we can separate 17 into this one, dt by root over 1 minus t square. This is a standard integral. Its integration is sine inverse t. Okay, minus 0 to 1 minus epsilon, this 1 minus t square, it cancels out. Okay, so it's root over of 1 minus t square, so here there will be dt, and so this evaluates to, so there is a standard formula for this also, root over 1 minus t square, integration is t by 2 root over 1 minus t square plus half sine inverse t. Okay, so that we have done, and this minus 8t, this can be written as plus 4 into minus 2t. I have written minus 2t dt here because if I take the derivative of the denominator 1 minus t square, derivative of the denominator is minus twice t. Okay, so it is in the form of dx by root x. Okay, dx by root x type of thing. Means I am not substituting anything here, mentally I am doing that. Okay, that is why I have converted it to this form. Okay, so you could have done it this way, that dt by root over of 1 minus t square. Okay, then substitute 1 minus t square equal to z. Okay, so minus twice t dt will be equal to dz. Okay, so like that you could have done, but once we convert it to this form, because minus twice, we need something like minus twice t dt. So if we already bring it here, then it becomes easier. We don't need to substitute, means introduce other variables. Okay, so we can just do it mentally. So it is in the form of dz by root z. Okay, so its integration will be 2 root z. Okay, integration of dz by root z. Okay, root over of z. So this is actually 2 root over of z. So this is what I have applied here. Then we can just put the upper and lower limit. So it's 17 sine inverse of 1 minus epsilon minus of this quantity, okay, and then we proceed to limit. Okay, so let us take the limit as epsilon tends to 0 plus. Okay, so it's actually, so sine inverse of 1 minus epsilon, so when epsilon tends to 0 plus, this will just be sine inverse 1. Okay, so that is pi by 2, and here this epsilon, here it will be 0, so it's half, and this is sorry, when epsilon tends to 0, this quantity will become 0. Okay, so you will be left with only this one, half sine inverse 1, so half pi by 2 again, minus 8 or plus 8, this one minus 8, sorry, because this quantity will become 0 and you have minus 1 here, so it's minus 8. So it's 33 pi by 4 minus 8. This is your I1. Okay, first integral. The second integral is you have to evaluate it from 4 to 5 minus epsilon. Okay, so that also we do it the same way. 1 minus of this. This calculation already we have shown in the first part, so we are just using that, and then again we are substituting x minus 4 equal to t. So it simplifies to this t plus 4 whole square divided by root over of 1 minus t square. Okay. So you see, if you observe carefully, it's what is this? This is 4 plus t square dt divided by root over of 1 minus t square. Okay, and here it is 4 plus t whole square dt. Okay, so only difference is in the sign of t. If we expand it, the difference will be just in the sign of 8t. Okay, others everything will remain same, right? It will be 16 plus t square, 16 plus t square plus 8t. Okay, so in the earlier case it was here it was 16 minus 80 plus t square. Okay, so everything else will remain same, only the sign of 80 will change. So the sign of, in the final answer also, only this sign of this 8 will change. Okay, everything else will remain the same. Okay, so that's why we can just write similarly as above. We will get it is 33 pi by 4 plus 8. Okay, so I2 is this. So I2 I1 and I2 both exist finitely. That means the original integral that is given to us is a proper integral. Okay, sorry, it's an improper integral, but it's convergent. Okay, so I1 and I2 both exist finitely, so their sum will be the sum of I1 and I2. Okay, so that's 33 pi by 2, right? Okay, so this was one problem. Another problem is this minus 1 to 1 dx by 2 minus x into root over of 1 minus x square. So here minus 1 and 1 are the only points of infinite discontinuity. So again we separate it into two parts. I1 is minus 1 to 0 of this, I2 is 0 to 1 of this. Okay, now we evaluate minus 1 plus epsilon of this one. Okay, so how to evaluate? So there is a system here, dx divided by linear root over of quadratic. Okay, so you have done these things in higher secondary. If you have this type of integral, then what you do, we take linear equal to 1 by t. Okay, so here this linear 2 minus x, we take it as 1 by t. So dx will be your 1 by t square dt, and we'll change the limits. So it will be from 0 to this 1 by 3 minus epsilon to half. Okay, so try to evaluate this. So it's t square. So everything depends on how good you are at integration. Okay, so you need to practice the integration things very properly. Okay, so all these things were actually done in higher secondary. Only the evaluation part, I mean, not the improper part. At least the evaluation part was done in higher secondary, so you should be able to do it. Okay, so t square minus of this. Okay, so if you just simplify, you see, you please try to do it yourself. I'm just showing you how you can proceed. Okay, so it's 1 by 3. So I'll conduct a live session also, where I'll give you some problems and I'll ask you to solve. Okay, so this is half of this. So ultimately it reduces to something like this: 1 by 3 minus 3 into this one. So this 1 by 3 I can take outside, so it's 1 by root 3 into this. So it is of the form dx by or dt by root over of a square minus t square. Okay, so something like that. So this integration is sine inverse of t by a. Okay, integration of this is sine inverse of t by a. Okay. So here instead of t you have something like t minus b. Okay, so it's all the same, it's t minus b by a. Okay, so that is the integral. So it's sine inverse of this minus sine inverse of this. Okay, and then if you take epsilon tends to 0 plus sine inverse of minus half, this will be minus pi by 6, and this is sine inverse of minus 1. Okay, so it's minus pi by 2. So ultimately it's pi by 3 root 3. So it's I1. Next I2 is this quantity. Yeah, so for I2 also ultimately you will get the same thing here. Okay, yeah, so for I2 also only this limits will change. Okay, so it's dt by root over of 1 by n minus 1 by 9 minus t minus 2 by 3 whole square. Okay, so that also will evaluate to yeah, so there will be some differences because of the limit. Okay, because of the upper limit and lower limit, there will be some differences. So it's pi by 2 plus pi by 6, so 2 pi by 3 root 3. So I2 is also there, hence both I1 and I2 exist finitely, so the original integral is convergent. Okay, hence so you may write this part also, hence the given integral is convergent. Okay, please add that part also. So their sum is actually pi by root 3. Okay, pi by 3 root 3 plus 2 pi by 3 root 3, the sum is actually pi by root 3. Okay, so another problem which I had given was integration of minus 1 to 1 x minus 1 by x to the power 5 by 3. Okay, so here the only point of infinite discontinuity is 0 actually. Okay, so let I1 equal to minus 1 to 0. So we separate it into two parts. One is minus 1 to 0. of this quantity, and another one is 0 to 1 of this quantity. Okay, so similarly we will evaluate. So this evaluation is quite simple, because we just separate it into two parts: x by this minus 1 by this. Okay. So it's x, then just apply x to the power n, integration of x to the power n dx. Okay, that formula we have applied. So it's something like 3 into x to the power 1/3 from epsilon to 1, and this is minus 3 by 2 x to the power minus 2/3 from epsilon to 1. So this, if we apply the limit epsilon tends to 0 plus of this is what? So it will tend to minus infinity. Okay. So why does it tend to minus infinity? For this part it's 0. Okay, but for the problem is with this part. When epsilon tends to 0 plus, 1 by epsilon to the power, this limit of this is actually infinity. Okay. So we have done these things in real analysis, right? Limit of x tends to 0 plus of 1 by x. Okay, this is equal to infinity. Okay, that means what? 1 by x can be made as large as possible when x approaches, by taking x close to 0. Okay, from the right side. So that is the meaning actually. So since this, so here you see this, which one we have taken? We have taken it from, yeah, we have evaluated the integral corresponding to I2. Okay, we have evaluated integral corresponding to I2. So, and we have seen that I2 diverges. So we don't have to check anything about I1. Okay, because if one part diverges, by definition the entire integral actually diverges. Okay, so we don't have to check I1, even if I1 exists, so we can't do anything about it, right? So that way you can solve the problems. Okay. The next part is actually the comparison tests. So many a times it's quite difficult to evaluate the integrals also. In that case, what we can do is we can use some comparison tests for convergence of these integrals. Okay, so what are these? So these are something similar to the comparison test for sequences. Okay. So let f and g be two positive functions. Okay, so for the comparisons we need them to be positive functions. Okay, such that fx less than or equal to gx. Okay, fx is less than or equal to gx for all x inside AB. Okay, and A is the only point of infinite discontinuity. Okay, then so if so here you see the function f is smaller than the function g. Okay, so integration a to b f dx. So if the larger function converges, okay, then the smaller one will converge. Okay, that is the comparison test. For sequences also it was something like this. Xn converges to, or the comparison test for series was there. Okay, if xn is less than or equal to yn, xn and yn are positive term series. If xn less than or equal to yn for all n, and summation yn converges, then summation xn also converges. Okay, so that was the thing, right? So it's something similar to this or analogous to this. Okay. So integration a to b f dx converges whenever a to b g dx converges. Okay, but I cannot say anything if this larger integral doesn't converge. Okay, but if the smaller integral doesn't converge, in that case I can say something. Okay, if the smaller one diverges, then the larger one has to diverge. Okay, that is the thing. So integration a to b f dx converges whenever integration a to b g dx converges, and integration a to b g dx, the larger one, diverges whenever the smaller one diverges. Okay, so the case when b is the only point of infinite discontinuity is similar. Okay. It's similar to this one. Okay, so this is the first comparison test. The second comparison test is we evaluate the limit when limit of the ratio fx by gx. So let f and g be two positive functions in AB, and A be the only point of infinite discontinuity of f and g. Okay, and if limit x tends to a plus fx by gx is equal to L, where L is a non-zero real number. Okay, so this L has to be non-zero. Then the integrals a to b f dx and a to b g dx converge and diverge together. Okay, so let me not write and, converge or diverge together. Okay. So if this limit, so this type of comparison test was also there for the series, right? If xn by yn limit it is equal to L, where L is non-zero, then the integral, the series converge or diverge together. Okay, and then that was already given. So this is also something similar to this. If we evaluate this ratio and then take the limit, if it comes out to be a finite quantity which is non-zero, then the integrals, these two, will converge or diverge together. That means if one of them is convergent, the other one will converge. Okay, if one of them is divergent, the other one will diverge. Okay, that is the thing. So it's a more useful comparison test here actually, right? Also, there is something which we can conclude when the limit is actually 0. So if limit x tends to a plus of fx by gx is 0, and the larger one converges, then the smaller one will converge. Okay, and if this limit is infinity and the larger one diverges, okay, then this also diverges. Okay, a to b f dx diverges. Right. So these two things you have to understand carefully. Okay. So a useful comparison, yeah. So we need some standard for comparing. Okay. So in many of the cases we can use this integral for comparison. Okay. So let us try to prove whether it converges or not. Integration a to b dx divided by x minus a to the power n. Okay. So this converges if and only if n is strictly less than 1. Okay. So this integral will act like our p series. Okay, summation of 1 by n to the power p. So that is convergent if p is greater than 1. Okay, divergent if p is less than or equal to 1. Okay, that problem was there. So this is also, so that p series usually we use it for comparison, right? So here this integral we will show that it converges if and only if n is less than 1. Okay, otherwise it diverges. So let us consider the cases one by one. So if n is less than or equal to 0, then see, if n is negative, what happens? Say something like this one, integration of dx by x minus a to the power minus 2. Okay, so this will ultimately become x minus a whole square dx. Okay, if n is less than or equal to 0, then this ultimately becomes this. So it is not a improper integral actually. Right, so there are no points of infinite discontinuity. Okay, so this is what I have written. If n is less than or equal to 0, then this integral is a proper integral, okay, which evaluates to, so we can easily evaluate that b minus a by b minus a to the power n minus n plus 1 by minus n plus 1. Okay, so for n less than or equal to 0, it is already convergent. Okay. Right, if n is strictly greater than 0, okay, in that case a is the only point of infinite discontinuity. Okay, so then also let us consider two different cases. One is for n not equal to 1. Okay, if n is equal to 1, what happens? There is a problem, means we cannot use this dx by x. This integration is not something like x to the power minus 1 plus 1 divided by minus 1 plus 1, because in that case this becomes 0. Okay, so this integral is actually log of mod x. Okay, right. So but so that is why we have to separate two cases where n is not equal to 1 and the case when n is equal to 1. So let n not equal to 1, then this integral is actually this one, it will evaluate to this. And if you put the limits and then take limit epsilon tends to 0, okay, in that case you see this first part, for the first part there is no problem provided 1 minus n is greater than 0. Okay, sorry, if 1 minus n is greater than 0, okay, then your this one, so the first part is constant actually, we are taking limit with respect to epsilon. Okay, so first part there is no problem, the problem comes with this part. Okay, so if the exponent or the power of epsilon is negative, okay, in that case I will get an infinite sort of thing. Okay, if it is something like 1 by epsilon, okay, 1 by epsilon to the power some positive quantity, in that case this will tend to plus infinity. Okay, So if the power is positive, in that case there is no problem. Okay, in that case this will become 0, right? So this is what I have written. If the power 1 by n minus 1 minus n is positive, then this limit is actually equal to this one. Okay, limit is exactly equal to this. And if 1 minus n is negative, in that case the limit is minus infinity. Okay, so the integral converges if n is less than 1. Okay, if n is greater than or equal to 1, if n is greater than 1, then it diverges. Okay, so the integral converges if n is less than 1 and diverges for n greater than 1. Okay, so we now consider the case, only one case is left, n equal to 1. Okay, so if n equal to 1, then it becomes log of this. Okay, so you can write log mod also. So here already we have written b is greater than a, so it's log of b minus a minus log of epsilon. But when epsilon tends to 0 plus, log epsilon actually goes to minus infinity. Okay, log epsilon actually tends to minus infinity. So here you have minus log of epsilon, so this actually goes to plus infinity. So this integral is divergent for n equal to 1 also. So thus in conclusion we can say that the integral converges if and only if n is strictly less than 1. Okay, for all other cases it actually diverges, right? So similar result holds for the convergence of a to b dx by b minus x whole to the power n. Okay, so you please try proving it also. This is given as a homework. You please try proving it. Okay, means if the point of infinite discontinuity is b, means the denominator is something like b minus x to the power n, in that case also the same result will hold. The integral converges if and only if n is strictly less than 1. Okay, so let us use this particular integral in testing the convergence of certain integrals. Okay, so test the convergence of this 0 to 1 dx by of this. So you see that 1 is the point of infinite discontinuity. So let us try to write 1 in such a way that we can compare it with something. Sorry, let us try to write fx in such a way that we can compare. Okay, so this fx is 1 by root over of 1 minus x cube. So I can write it as 1 divided by root over of 1 minus x into 1 plus x squared. Okay, the formula for a cube minus b cube. And then I can separate it as 1 by root over 1 minus x into root over of 1 plus x squared. Okay, now you see if I can write it something like less than or equal to 1 by root over of this or greater than or equal to, okay, then the comparison will happen. Okay, so here we have x is a element in this 0 to 1. Okay, x lies between 0 to 1, so we have 1 plus x squared is greater than or equal to 1. Okay, right, x is greater than or equal to 0, x square is also greater than or equal to 0, so 1 plus x square is always greater than or equal to 1. So from there 1 by 1 plus x square is less than or equal to 1. So this quantity is always less than or equal to 1. So ultimately using this I can write fx is less than or equal to 1 by root over of 1 minus x, but this can be written as 1 by 1 minus x to the power half. Okay, so we have got our comparison integral, that is gx. Okay, the function with which we will compare. So let gx equal to this, and then fx is less than or equal to gx for all x inside this, right? Then what happens? But integration 0 to 1 dx by 1 minus x to the power half converges. Why does it converge? We have used that result. Okay, integration dx by a to b minus x, okay, to the power n. This result we have used. It converges if and only if n is less than 1. Okay, so here n is actually half and half is less than 1, so it actually converges. Okay, this. So by comparison test, integration of 0 to 1 dx by root over of 1 minus x cube, this also converges. Okay, so this is how we can use this. Okay, similarly let us try this 0 to pi by 2 sin x by x to the power p. Okay, so for p less than or equal to 0, the integral is actually proper and converges. For 0 less than p less than or equal to 1, we have the limit of this is actually 0. Okay, how the limit is 0? We have sin x by x to the power p. This can be written as sin x into sin x by x into x to the power 1 minus p. Okay, I can write it this way, right? So since p is less than or equal to 1, so this quantity is converges to or tends to 0 as x tends to 0 plus. Okay, and sin x by x, that limit is 1. Okay, so this tends to 1 into 0. Okay, the limit of this is 1 into 0. So for 0 less than p less than or equal to 1 also, this integral is a proper integral. Okay, it's not improper. So something like sin x by x, this is actually a proper integral. Okay, because there is no point of infinite discontinuity, even though x is in the denominator. Okay, because of this sin x by x type of thing, it becomes a proper integral. So we don't have to check anything for p less than or equal to 1. Okay, so for p greater than 1, we have 0 is the only point of infinite discontinuity. Okay, so we will write fx as and something like this, sin x by x into 1 by x to the power p minus 1. Okay, so we can compare now. Sin x by x, this is always less than or equal to 1. Okay, this sin x by x quantity, this is always less than or equal to 1. Okay, so we can write it as less than or equal to 1 by x to the power p minus 1. So we take gx as x to the 1 by x to the power p minus 1. So under what condition this integral converges? Integration of dx by x to the power p minus 1, it will converge only when p minus 1 is strictly less than 1. Okay, that is p is strictly less than 2. Okay, that is the thing. So 0 to pi by 2 dx converges for p minus 1 is strictly less than 1. So that is for p is strictly less than 2. So by comparison test, this integral also converges for p less than 2. Okay. So but what happens when p greater than or equal to 2? So let us use the second form of the comparison test. Yeah, for p greater than or equal to 2, what are the possibilities? Let us use this second form, limit x tends to 0 plus fx by gx. Okay, so in that case, sin x by x to the power p divided by gx is 1 by x to the power p minus 1, so that goes above. So this becomes 1, which is non-zero. That means this integral and this integral converge or diverge together. Okay, but for p greater than or equal to 2, we have p minus 1 is greater than or equal to 1, so that this integral actually diverges. So this integral converges if p minus 1 is less than 1 and diverges if p minus 1 is greater than 1. That is converges if p greater than or equal to p less than 2 already we have seen. Okay. Oh no, what I was saying is, yeah. Okay, so the first way of doing it actually gives us this up to this. Okay, but we need to conclude something more, so that is why we can use the second form of comparison test. So in the initial part itself, you could have used second form of comparison test, then we get the results very nicely. Okay, in the first form, you see, we have to write it less than or equal to something gx. Okay, and then conclude about the convergence or divergence. Okay, so for p greater than or equal to case, it's already it's not clear from the first comparison test. Okay, so we can, if we use the second comparison test, second form of comparison test, then in that case, you see, this limit is actually equal to 1, so which is non-zero. So these two integrals converge or diverge together. So we can conclude about the entire convergence using this second form of comparison test itself, because this integral will converge if p minus 1 is strictly less than 1 and diverges if p minus 1 is greater than or equal to 1. So that is the original integral converges if p is strictly less than 2 and diverges if p is greater than or equal to 2. Okay, so that is the thing. So in the earlier one, what we had done is, for p greater than 1, right, this is the only point of infinite discontinuity. Yeah. So in the first case, why we cannot conclude anything by the comparison test? Because we know that this integral converges if p minus 1 is less than 1, but diverges if p minus 1 is greater than or equal to 1. Okay, that is p greater than or equal to 2. But even then, I cannot come to any conclusion regarding the convergence of integration 0 to pi by 2 fx. Why? Because it's not guaranteed. Okay, there may be integrals which satisfy this fx less than or equal to gx, and the larger one is divergent, but there are cases where this may be convergent. Okay, this one may be convergent. Okay, say something like what should I say? Say fx equal to 1 for all x inside fx equal to 1 for all x, right, inside. I have not done the year thing. No? Yeah. Okay, or say fx equal to 0 for all x inside say 0 1. Okay, and then I take gx as this function 1 by x to the power this x square, 1 by x square. So this integral doesn't converge. Okay, it's divergent because n is greater than 1. Okay, so but 0 is already less than or equal to 1 by x square for all x inside this. Okay, so the larger integral diverges, but the smaller integral converges because it's the constant. Okay, it's just 0. Okay, so that is why from the first part I cannot conclude anything when this is divergent. Means for p greater than or equal to 2 case, I cannot conclude anything from the first comparison test. Okay, but from the second comparison test we can conclude. Okay, so in the earlier one, what we have done, the earlier one, so earlier one we had a fixed power. Okay, so that was not a problem. Here the power is a variable. Okay, x to the power p, so that creates the problem. So if p greater than or equal to 2, we cannot conclude anything from the first comparison test, so we have to go for the second comparison test. Okay, so while in exams you can just directly start with the second comparison test itself. Okay, it's easier if you in some cases at least it's easier. Okay, so I give you a homework. You try this. Find the values of m and n for which integration 0 to 1 e to the power minus mx into x to the power n converges. Okay, so for what values of m and n it converges. Okay, so please try it. We will sit for a live session. I'll let you know. Okay, then we'll do other problems. Thank you.